This is a pendulum. It was first used by Galileo to try to create some math equations. It's essentially just a mass, or in this case a cup, attached to a string. So you'll find that whenever you pull it a certain direction, you have this force pointing this way along the string, or the tension of the string, which is essentially just keeping it on its rotation. And then you also have the force of gravity pushing down from the mass. And so whenever you drop it, you find that it swings back and forth like so. This is what the free body diagram will look like. So you see that the force of the tension or string is pulling one way, and the force of gravity is pulling the other way. Whenever you swing a pendulum over a graph between theta and time, it makes a graph like this. Here, I'll show you. Some important vocab to know about waves before I get started with some math is that period is from one point to the very next. It's just simply one rotation or one cycle. The amplitude is from the top of the trough to equilibrium. And then, which as you can see would be when theta equals 0. And then the wavelength is from the bottom of a trough to the bottom of another. Whenever you have a high frequency, you tend to have lower wavelengths. And vice versa, whenever you have a low frequency, you have longer wavelengths. So I decided to conduct an experiment to see if I could predict the frequency and period of one of the graphs we just discussed. So for my string length, I had 0.7747 meters, which is about 30 inches. And then I had a mass of 0.01 kilograms, or about 0.02 pounds. And as you can see here, I just wrote down some general guidelines for periods and frequency that I'll just use for some labels later on. So initially I decided to solve for frequency. If you look at the formula above, you'll notice that there's no theta and there's no kilograms, because for the G represents gravity rather than the force of gravity or the weight. This is because the mass cancels out in the derivation, and because of the small angle rule or theorem, which basically says that if you have an angle that is less than about 10 degrees and you are using sine, which we would do if you think back to free body diagrams to calculate one of the components in the y direction, that kind of gets discarded. It was in the original derivation, but because of the small angle theorem, because mine was 5 degrees, it would be negligible. So I wrote down the things that we know, and I just plugged in and solved. So I ended up getting my period being about 1.766 cycles per second, which, if you look at the video, is pretty good. Here, I'll show you. Just a heads up, I slowed the video down, so 1 second in real time is about 8 seconds in my video. So, like I said earlier, my period actually ended up being on pretty well in terms of the 1 second. So it looks like here that it isn't too hot, because you can see 1 second is marked there if you look at the video, and the second is marked here. And so you would think I'm actually pretty off, but really I wasn't very good at pulling the cardboard consistently. So since I already had my period figured out, I figured out that I'd just figure out frequency while I was at it. I ended up getting 0.56606 seconds per cycles, which I really struggled with because it didn't really seem to match up, but once I started thinking about it, it started to make sense. So when looking at the frequency, I already discussed it. It's kind of related to wavelength, which you can see I have marked here on the bottom. And the wavelength here, and the frequency in total that I figured out, is not related to the wavelength at all. It doesn't seem to make any sense, but judging by the fact that I pulled it at not a constant rate, in fact I pulled it a little too slow, it makes sense. A lot of times whenever we're doing problems like these, we're looking at ideal situations. So for example, here it is an ideal simple pendulum that I'm looking at, and the resulting graph, which actually It's not too bad if you ask me. We do not take into consideration things like friction between the rope and the pole I tied it around for the axis, and the air resistance. So it makes sense that some of my numbers would be a little off. Another thing to take into consideration that I was just thinking about is, remember at the end, whenever it started kind of spinning in a circle? I cut that part off, but I'll show you in the video here. So that tells us that whenever it moved in a circle, that there was some oscillating motion as well. It wasn't exactly just back and forth like you would have in an ideal situation. So that could also affect things like the wavelength and the period. So like I mentioned earlier, pendulums used to be used for math and clocks and stuff like that, but now they're really used more for art and kind of those artistic outlooks. And so I decided, I already had paint out and, might as well give it a try, and not as easy as it looks, but I did get one piece is not complete trash, so I call it a win. Oh my gosh, you let go of it. Oh no. Oh no. Oh no, you didn't let go of it straight. Now it's going in circles.